Welcome back. In today's episode, there are two parts. So one part is where we're going to pull a data set from memorizing transformers, and we're going to process it and split it up and really prepare it for our specific application in memorizing transformers. But the other part I want to talk through first is a more general discussion of how to get your data, store it, process it, and then load it efficiently. So that is the data processing pipeline that I want to talk about. So we will look at our specific use case for memorizing transformers, but I didn't feel that it would be a very effective way of teaching you about this stage of building a model from scratch. So I want to give you a general strategy before we just work on a specific application. So we'll step back a bit and get a principled approach, because you'll find that the requirements for data loading and processing change a lot depending on your data set, your model, the hardware you're using. So really, it's hard to have a one-size-fits-all data processing pipeline. Therefore, a principled approach is going to help you a lot more. And I also want to do this because I've personally always hated this part of the process. And I know I'm not alone. It's always, to me, been a very finicky, one-off, kind of annoying part of building a model. So I want to share some pictures and principles that have helped me hate this process much less. So here's the process I'm talking about. We have 4 simple steps. Get our data set, store and load the data somewhere, process and tokenize the data, and then load a batch of data and send it to the GPU. What is annoying here? So loading data, step 1, used to be actually quite a problem, but it's less so nowadays. So nowadays, I would say you can go to something like Hugging Face's datasets or TFDS or one of these other libraries, and really a lot of different datasets are hosted here. And it's very clear what's inside. The formatting is very clear, and it's very, very easy to pull this. So you can very easily download it. You don't have to go, hunting for a script or asking for permission for a data set, and then, you get a strange file format and you have to reformat it, and maybe it comes in chunks and you want to merge the chunks. So there's a whole pipeline that was very annoying, and you had to often tweak these custom scripts. So I would say step 1, not that much of an issue these days. Steps 2 through 4, or you might have larger issues. So it depends a bit on the tool that you're using, but I find the interface is usually at a very high level of abstraction. The interface for loading a data set and kind of sending it to your GPU. So this is very nice, but as soon as you need to do something kind of custom, this very high level interface breaks down. So you might get these very low level detailed errors coming back, and you've got this kind of black box interface that you work with, and it's not clear how to fix what's going on inside of it. So for Torch, for example, we have the dataset and the data loader. And these are 2 utilities, and when you just start learning, basically you see, okay, I just wrap my dataset in a dataset object, or in this case, we're loading it directly from Torch. And then I wrap that dataset object in a data loader, and it kind of takes care of all of this for me. So steps 2 through 4 kind of just get rolled into 1 or 2 different interfaces, and it's very high level. The problem is something goes wrong, or you need something custom, and you get thrown into the deep end of trying to figure out, well, how do I fix this, or how do I change this, or what's going on inside? And part of this deep end is diving into the documentation of these kind of high-level interfaces. So if you need to do something custom with your Torch data loader, for example, or you get some error, or it's too slow and you need to speed it up, you can come into the documentation and take a look at the data loader. And you'll find all of these configuration options, like number of workers, which enables multiprocessing and scales the number of processes for multiprocessing, pin memory. There's a lot of these configuration options, and unless you have a good kind of big picture understanding of what's going on and what your bottlenecks are, it's very hard to make sense of how to use these. And once you start asking about these kind of questions, say for optimization and getting your data where it needs to go quickly, you start having these adjacent questions like, does data loading work asynchronously with the GPU? So while the GPU is running, am I concurrently preparing the next batch of data? And where is that option here? Do I use an iterable generator, or should I just load my data set into memory? Should I set up some kind of custom buffer because I want to have pre-processed data stored somewhere so that I can quickly send it to the GPU? Or maybe should I pre-process and pre-tokenize my data set instead of doing it on the fly? Will that give me a kind of speed up advantage? Should I memory map the file? There's just a bunch of these questions that start exploding about different ways of optimizing this data processing pipeline. And because it's all wrapped up in this high level call, you have a learning curve of diving into the documentation and looking at a lot of PyTorch forums like I have to figure out what optimizations, for example, the data loader is doing by default, and what you have to configure for yourself. So you want to avoid that. So we can avoid a lot of this confusion by reminding ourselves of the big picture of what's going on. So this is a very basic understanding of what's going on here, but it should give us enough overarching detail that we can then dive down deeper wherever we need to optimize. So here's the basic diagram of what goes on, and here's what we need to remember. The GPU has the model in its memory, and we feed data from the CPU into the GPU where it gets processed. So send a batch of data from the CPU to the GPU, it runs through the model. When it's done, we send another batch of data from the CPU to the GPU. That is the picture of our model training. So what do we need to do to make sure that training is fast? We need to keep track of the distinct steps, identify which step is the bottleneck in our training, and optimize that step. And that is our performance cycle. We just repeat this over and over. And I hope that sounds obvious and self-evident, but sometimes because the data loading and processing interface can be very high level, you lose track of how to accurately identify and accurately remove bottlenecks. So profiling is your friend, and keeping in mind what is happening at every stage of data processing is your friend. So first, the GPU. Suffice it to say, the GPU optimization and internals are a topic of their own that we're going to get to later. But for our purposes right now, we're just interested in the dataset processing pipeline. So we're going to think of the GPU, an iteration of one batch through the model. We're just going to think of it as a fixed unit of time. And we're going to talk about everything else today, the dataset processing pipeline, relative to that fixed amount of time. A great resource that I want to mention here that's related to what we're talking about is this blog by Horsey. And it's all about making sure we can train fast, and that means maximizing the utilization of our GPUs. And really, this breaks down to identifying the bottleneck in your training loop, accurately identifying it, and then removing that bottleneck. And so part of this is that you don't want to be throwing optimization or resources at a part of your pipeline that won't actually be affected by more resources or more optimization. So a good example here is that you might have a slow training loop and you think, I'll throw more GPUs at this. But in fact, more compute won't help you solve anything because in many cases, the act of moving data back and forth between GPU memory and the actual GPU computation is what's taking up all of your training loop time. So just doing the computation faster won't make much of a difference because it's already a very small fraction of the time. So you might be spending actually all of your time in bandwidth costs, that is shuffling data back and forth. Therefore, more computation doesn't help, and you actually need a different kind of solution. And you only do this once you accurately identify what the bottleneck is. So it's a great post, and you'll learn a lot, and the principles he talks about apply to the data processing pipeline. So for our purposes, as I mentioned, we'll just treat one GPU iteration as a fixed amount of time. Someone else is working on GPU optimization. Our subworld of optimization here today is just to process the data set and send it over to the GPU. So the time it takes our data processing pipeline to generate and send a new batch of data, this just needs to be faster than the time it takes for the GPU to process that batch of data. So our job today is to make sure that the GPU is always the bottleneck. We're always sending data over faster than the GPU can process it. So let's take a look at the data processing pipeline and some of the optimizations that we have for it. And really, this helps us stay organized because every kind of optimization or configuration option you have will typically fit pretty nicely into one of these buckets. So what you first need to do is, once you've got your model running and you've got the data processing pipeline running, so you've got a data loader, whatever it is, you want to profile it and find out where your bottleneck is. And so it could be in the loading of data. So this involves taking data either from disk or from memory and loading it into memory where we're getting ready to process it. And if this is the slow part of your pipeline, then you can do something like memory mapping. You can maybe shard the data set if you're reading it from disk and have smaller shards and load the shards into memory. So there's a lot of optimization options you can have here. But the point is that you accurately identify this is what's slowing us down. The second step is processing data, and this really just means, for our case, tokenizing. So here the data is going to move from the CPU memory. It's going to go through the CPU as it's tokenized, and then this is put back into CPU memory. And so here, just some optimizations you could do is, if this computation step of tokenizing the data is what's taking long, then you can consider pre-tokenizing or pre-processing the data set. And you store this pre-processed version and then you load it directly. So you don't want to pre-process things on the fly if this turns out to be your bottleneck. You also want to make sure you're batch processing. That is, you're sending in multiple examples at a time for tokenization, because most tokenizers are built to do this more efficiently than one at a time. And then multiprocessing and async are very important here. So in fact, the async and multiprocessing kind of speak to all three of these steps, but a very, very important part of the data processing pipeline that I think you should always ensure is on or active, no matter what tool you're using, is this asynchronous and in some cases multiprocessing. So you don't want it to be the case that you send a batch of data to the GPU, it runs through the model, and only when it's done running through the model, the GPU says, I'm ready for more, then you start pre-processing a new batch of data. Once you've sent a batch of data, you ought to already be working on a new one, or rather, you want to have multiple going at the same time. So basically, you're always ready with pre-processed batch data that you can send to the GPU. And so this is very important to turn on, and in most cases, you always want this, unless there's some kind of dependency. But for this kind of application, that shouldn't be the case. So the last step here is send to GPU, and here we take the processed batch data from CPU memory and send it to the GPU where it gets trained. And one of the optimizations here is something called pinned memory. And this is essentially saying inside of the CPU memory, I'm going to have this fixed place where I put all of this batch data, and it's not going to get moved around. Whereas typically, data is moved around for all kinds of reasons to make room for other processes. It's moved to disk. That doesn't happen with pin memory. It's just going to stay here, and it acts as a staging area so that when it's time to send this to the GPU, it doesn't have to hunt down the batch data. It's all right there, and it can send it over to the GPU. And I've included some very, very accurate descriptions of how fast data moves between these different components. So these are qualitative assessments, and it depends on your hardware entirely, but in general, this kind of hierarchy holds. And so this is a very broad architecture. If you are diving into it, you can split each of these into more steps. But this gives you a good high-level place to start looking. And lastly, I'll add that these optimizations are not exhaustive, but they're just something that you can try without too much effort. Okay, let's just summarize and recap our process here. The point is to make training fast. As Horace says, make GPUs go burr. So our goal here, since we're just focusing on the data processing pipeline, is this. Make the time to process a batch of data less than or equal to the time it takes the GPU, or it takes the model to run that on the GPU. So that is the goal, and if you've accomplished it, you don't really have to think about optimizing or changing your data processing pipeline. So the bottleneck is the slowest part of your training loop. This is our methodology. Identify the bottleneck, remove it, repeat. The GPU should be your bottleneck. This is really because GPUs are expensive and hard to get a hold of. So you want that to be the limiting factor in your training. So we don't want a CPU bottleneck. You want to load a batch of data faster than the GPU can process it. This makes sure the GPU is never idle and it's always has a new batch of data to work on. If your GPU is sitting idle, then you want to optimize the data processing pipeline by profiling. So you profile, you accurately identify which step is the bottleneck, and you apply optimizations specific to that part of the pipeline. So I want to share a success story that demonstrates how this worked for me recently. For a side project, I wanted to pre-train a model with the C4 dataset. And the C4 dataset is a version of the common crawl dataset. And this is some examples here, but it's basically data pulled from the web. And the dataset is enormous. It's, I don't know how many terabytes, but it's much bigger than anything I could ever fit on my hard drive. So you might say that sounds unnecessary because I'm just going to be training a small model, but let's see if we can do it. Let's see how it works. So how are we going to tackle this? It sounds like a pain to take this data set that's enormous and efficiently load it. And every publicly available script I could find is kind of wickedly complex because it's feeding this into big clusters, and it all looks very daunting. So starting out very simply, I'll just stream the data set, which is an option I'll show you soon, but it's something allowed in Hugging Face where you add a parameter here that just says stream equals true, and you'll see this soon. This is where you download examples as you need them. So it's like a generator that pulls one example at a time, but from a Hugging Face server somewhere. So it's obviously very slow. It's not optimal. So I was jumping ahead and doing these optimizations and worrying about the wrong thing. So instead, I took the principled approach, followed the process, and profiled the training loop before trying to dive into all of that. At first, data processing was indeed the problem. It was too slow to load data. But specifically, the GPU was sitting idle and waiting for new data, not because of this very slow method of loading the data, but it was actually because it wasn't processing new batches of data asynchronously. So after ensuring that the data is being processed asynchronously, as embarrassingly unoptimized as the dataset streaming is, it was actually fast enough. And even after squeezing out optimization of the GPU in the training loop, it's still the bottleneck. So That's great news because the GPU is the limited resource, so I want to be making full use of it. And because I can continue this very lazy, simple way of pulling a data set that I was afraid would be, very complicated and unwieldy. So all of this to say, if you keep the steps in your pipeline clear and you can accurately identify bottlenecks, you'll be able to prioritize the right things and save yourself a lot of headaches. And this is what will make you hate the data processing pipeline less. At least that's what worked for me. Okay, on to the data loading for memorizing transformers. Okay, so we're finally ready to start building. So the first thing that we're going to do is download our data set, and then we're going to implement a really simple training loop. And this will give us a way, once we've built our model, to really quickly and effectively test it to make sure it's working and see how well it's doing. So this is a really important first step in our pipeline. So I've downloaded a few libraries here, NumPy, Torch, a couple Torch utilities, which we'll get to later, and the datasets library. So the datasets library is from Hugging Face, and I recommend it as a way to pull datasets that are hosted there. So this and TFDS, which is like a TensorFlow equivalent, just allow you to very quickly download a dataset instead of maybe having to hunt for it and then convert the file format, this is all not fun stuff. So we're going to be using this. And the dataset I've chosen, and I looked around for a few, and I came up with this one. It's archive summarization. So this contains a lot of archive articles, and they're about everything. So this one is about laser light scintillations. This one is about nucleon spin crisis. This one is leptonic decay. So just a bunch of papers from a bunch of different topics. And we've picked this one because these are long documents. All of these articles are thousands of words long. And if you remember, the whole point is that for this model, the memorizing transformer model, we want to take a very long document that is longer than the input size of our model, break it into chunks, and with each successive chunk, look backwards and see if we can find information either in the XL recurrent memories or in the KV stored memory that will help us model the language of the new chunks. So we need long documents that can be split into chunks that we can feed through successively. And this is a good model, or rather a good data set for this. So let's download the data set. Just to show you a useful parameter here, if we try and download the data set like this, which is really the recommended way, you will in fact be downloading the whole thing. And this is okay, but for our case, we end up sitting here a little while. And so every time you load this, you might not want to sit and wait through the whole thing. So a handy parameter is streaming equals true. And this will make it sort of act like a generator where it will only take data as you call for it. And in this case, we're going to use the train split because there are already 200,000 articles in the training split, so that's more than enough for what we need. So there we go. And we don't have to sit here waiting. We will take 3,500 articles here. So this will take a little while, but not nearly as long. Now, I want to talk a little bit about the format of what we're doing. So in a typical training pipeline, you download your data set and you shuffle all of these pieces of data and you feed them through. And it doesn't matter in what order they are fed into the model. In fact, you don't want them to be fed in sequentially in case there's some kind of bias in the distribution of your data set. Like if you have a big news data set, the first third might be sports articles, and the second third might be fashion articles. And so your model will be learning different distributions of news articles as it goes. So we always try and shuffle our data set as we feed it through. In this case, that's not what we're doing. We in fact are doing the opposite. We want to feed in the same article chunk by chunk. And so how will we do this? The desire here is something like this. And if you remember in the paper, they talk a little bit about their data sequence for feeding this into the model. And this is a little confusing, so I'll expand upon it a little bit here. Let's say we have a batch size of 4, and we're going to call it a chunk size of 5. What this means is we're going to have 4 samples going in, and each is a separate paper. But before we feed the paper in, we actually have to chunk it into window size chunks. So the first forward pass is going to be the first chunk of each paper. And each of these 4 papers represents the 4 numbers of the batch size. And so each batch will be the first chunk, and then the second chunk, and the third chunk, and so on. And when we're done with this paper, because we've run out of, say, tokens after chunk 5, we feed in new papers, and we start over. And so there's a slight difference in that what they propose is a little more natural. All papers are different sizes, so you wouldn't expect necessarily document A and document B to be the same size. So you would have some discrepancies over how these got split up. This is a little more natural, but it introduces a few problems, or rather a few complexities, that we can do away with for now and actually just build in later. For example, if one document is not divisible by our chunk size, we'll actually have to go in and pad it. And then we'll have to have a specific way to tell, for example, batch size 1 that it's done and it needs to fetch a new paper. So this is all doable, but we're going to make things simple on ourselves. And so what we're going to do is say that we want each paper to be 10 segments, and we want to have a segment length of 512, meaning we'll feed through 512 tokens into the model. Then our chunk size is these two multiplied by each other. So we're going to pull 5,120 token chunks out of our papers. Okay, so our data set is loaded. Let's take a look at it and do a little pre-processing. Take a look at the first example. And this is on semi-parametric regression. Great. And there's both an article and an abstract. And so we only want the article, so we'll get rid of the abstract. This dataset is probably intended for a summarization model so that you can compare the full-length article against the abstract and use that as a proxy for how well your model can summarize. But again, we just want the abstract, or rather the article. So we also want to filter for chunk size. So we already know that anything smaller than chunk size won't be useful to us because we're going to break every long article up into a chunk size of 5,120. So if it's a multiple of 5,120, that's great. Then we'll make multiple chunks out of that one article. But anything that in its entirety is smaller, we won't be able to use. So we're going to discard that. And the tokenization scheme we're going to use is just a character tokenization scheme. So there won't be any subword or full word. We're just going to start very simple and have a character tokenization. So this means we can simply filter by the length. Let's see how many we have left. Okay, 3,401. So out of 3,500, that's fine. So we'll want the tokenization set. And then let's also see all of the strings, or rather all of the unique characters. Let's sort that just so we can see a little better what's going on. Okay, so we have 3,400 articles that are above 5,120 characters. And we're working with this character set. So we'll have an embedding size that needs to be at least 70. Okay, so it's time to convert the characters in our dataset into numbers that the model can actually work with. So we'll take the first article and convert it. We'll convert it into an unsigned 8-bit integer. So this is mapping our character set onto 128 integers. We have a character set length of 70, and this is being mapped onto 128 different integers. You can call ord and see that the exclamation point maps onto 33. This maps onto 126. So each of these have a different integer representation. But we only have 70 characters and 128 slots. So this will be slightly wasteful in that when we convert these into embedding vectors, some of these embedding vectors will never be called. They will just be dead embeddings. On the other hand, this is a very simple scheme, so we'll stick with this for now, and we can always come back and change it so that it might adjust for new data sets that have a different character set, or likely when it comes time to really finalize and fine-tune the performance of this model, we won't use character embeddings. We'll use something like byte pair encodings or subword embeddings. So for now, this is okay. And just to show you that these integers map back onto the original text, we have a decode from integers back to characters. So we can see that this should map onto additive multiples, excite. Okay, so we have our encoding scheme for turning characters into numbers and back again. Okay, we finished our very sketchy tokenization scheme. So now it's time to turn all of our articles into a tokenized format. Okay, great. So now we actually need to put our articles into the appropriate chunk size. So if you see here, we have 5,120 is our desired chunk size. So when it comes time to feed something through the model, we want 5,120 characters of the same article, and we're going to have a batch size, say, of 8 of them. And we're going to take these and split it into 10 chunks. So instead of feeding 5,120 characters through the model, we're going to split them into 10 chunks and then feed those through. But first we need to make sure that all of our articles are a multiple of 5,120. So right now they're whatever natural length they were. We're going to take the remainder of the article relative to the chunk size that's desired, and then clip the article at that point. So we just cut off the remainder. And so what remains is articles that are either 5,120 characters or 10,024 characters, and so on. So we'll have the multiples. Let's take a look at this first one. Fair enough. It's 25,600 characters, and we want to see if it's divisible by 5,120. Great. So we get 5 chunks out of the first article, we get 3 chunks out of the second article, 5 chunks out of the third article, and so on. So everything has become a multiple of 5,120. And this will allow us to evenly take one long paper and make many training examples out of it. So we want to actually chunk these longer multiples of 5,120 into exactly 5,120 length chunks. And because the articles are now in a NumPy array, we can just reshape them to the desired length. So reshape will take an array of some size and reshape it to the desired dimensions that we want. So we want each one to be converted into chunk-sized chunks. And the -1 here just says whatever makes chunk size possible, make that -1. So the total shape divided by chunk size, this will fill in whatever that number is. So this could be, for the third article, it will be 5. For our first article, again, it'll be 5. For our second article, it'll be 3. So this will automatically break them into appropriate size chunks. And then we want this for and we're doing list comprehension inside of a NumPy array. That's not the cleanest thing ever, but we should be all right. And now, finally, we're going to turn this into a torch tensor, which is the format we've been looking for. And so here, concatenate is just basically allowing us to take this first document that was chunked into 5 next to this one that was chunked into 3. So inside the array, we actually have a 5 by 5,120 and then a 3 by 5,120. And this flattens all of those out. And we convert it into a torch tensor, and we make it type long because that is what we will be working with. Okay, so after all of that, we've finally got our data in a place that is useful to us. So we have 20,853 examples of articles, or rather sequences of articles, that are 5,120 characters long. So each of these will be used to feed into the model, and as it's being fed, it will be broken into 10 chunks and fed in sequentially. Okay, so we finally processed our data. We've got it in the right shape. Let's take a look very precisely at an example of how this will be fed through the model. So I've called data loader here, which is a torch utility we imported early on. And this essentially just wraps our data set and gives us some functionality and parameters about how we want to feed it through. So this makes it very easy to feed your data through a training loop. So I've selected batch size of 8 and decided to shuffle and wrap this in an iterator so that we can call a single example. This example is batch 8, so we have 8 examples that are 5,120 length characters. And now we need to make sequences for training and labels for each of these. So we do that by taking the example, and for all batches, the sequence that will be used for training contains all tokens except for the very last one. And the labels will contain the whole sequence except for the very first one. So if we take a look at our first example, these are the numbers that correspond to characters in our training set. So this spells out some word. And we're going character by character, trying to predict from 1 what the next one will be. So based on 102, we want to predict 114, then 97, then 99, and so on. And so if you look at the labels, this is just shifted 1 backwards, so that for the first example, we know that the target is 114, which is exactly right, because it corresponds to the next character in the original sequence. And for 114, we want to predict 97, which is correct because that's the next character in the sequence. So this looks good. And each of these will have a length of 5,119 because it's either missing the first or the last character. But remember that we don't want to feed in 5,120 characters. We want to feed in chunks of 512. So chunk will split this into 10 chunks as we've requested. And so this will create, for each of the 8 batches and the 5,120 character length, it'll create 10 different training sequences. And so if we look at these together and we decode them, we can get a good look at this, hopefully. I don't know if this article will help us. But here we're saying this is the 0th batch. And so for each sequence segment in the 0th batch, we should be seeing the same paper continued one after another. So for every continuous function at x math 578, that doesn't help us. All right, we're going to try the next paper. And again, there are 10 chunks of this because we're looking at the second batch that is broken into 10 chunks. Exactly solvable models. Despite the success, the application of the exact solution, so we can see that this is successful. Systems. Great. Okay, so now we've got a really good idea of what our data looks like and what it will look like as it passes through the model. So all we need to do to finish our pipeline is to add a training loop and a test model so that we can make sure that everything works end to end. So I've created a toy model that I will put in here. And we don't really care what this model does. I just made it up pretty arbitrarily. It has an embedding dimension of 128, which is important because our character set is 128 vocabulary size. And it also outputs 128. So that's what matters. It goes through a couple of layers. We don't really care what's going on inside of here. We need a few tools for our training pipeline. A loss function for cross entropy. We have an optimizer, and again, we don't care too much right now. We're going to use stochastic gradient descent with a made-up learning rate and tell the model to train. And segments refers to the fact that we'll be taking 5,120 length sequences and segmenting them into 10 chunks. Here is our training loop. And I'll walk through this quickly. But in general, much of this should look very familiar if you've trained a PyTorch model before. The training loop is very boilerplate. All of the steps should be very familiar. So for ion range 200, we pull a piece of data from the loader and we split it into sequences and labels, remembering that this is offsetting the data by 1 character. And this is the perhaps only unusual part about this training loop, is that there's an inner loop. So one piece of data is 8 batches of 5,120, and here, in fact, we segment this into 10 passes of 8 by 512. So the inner loop creates 10 passes out of 1 call of data. We flush the gradients, run the model through, and we need to transpose the predictions or the logits. So we're just switching the dimensions here. This is just the requirement imposed on us by the loss function. Step backwards, optimize, so run the loss backwards rather. And then we step with the optimizer, and we have a way of printing out to see what the model is doing. So we'll give this a shot, and it should work. And it does, so it runs, which is really the only important part. And the numbers are going down, which is also a good sign, even though we don't care for this model. These are all made up numbers. We're not tuning any of these hyperparameters. This is simply there as a proof of concept so that when we do build memorizing transformers, we will switch in model here, and we'll be calling a different model. So that's really all we'll have to do. This part of the pipeline is done, and so we can finally get on to building memorizing transformers.